All right, so I got to pop this data in. I, in my career, never figured out a way to seamlessly transfer data to student calculators for like a test or even classwork. There are ways to do it. It just requires me to link up with every one of your calculators. I'm not going to do that. Not on a daily basis. There were some calculators that had line of sight, where if you pointed the calculators towards one another, you could transfer files over the air. But then I found out that people were transferring answers to questions over the air during a test, and so that went by the wayside. All right. It's good. Hardest part of the test is over. It's all relative, I guess. Yeah, no, if you have properly annotated index cards with step-by-step calculator stuff, that might be a true statement. Right? Like, really, I mean, it could be a matter of just making sure you get the data in right, because everything else is very procedural. So the first task is going to be to create a frequency table and a frequency histogram for the data. Right? So data's in. You're not going to have to retype data for a few problems down the line, like until you get to like the sixth question or whatever it is that you have to retype data. So I want a frequency table, a frequency histogram. So we kind of do this backwards on the calculator. So your title for your X column could be specific or it could just be X. It doesn't matter to me. I need you to have labels. I'm not overly particular about what type of labels you use as long as they correctly reflect the data set. Right? And X and F is perfectly fine. Probably not a bad idea to get the labeling out of the way immediately to avoid forgetting it. So just a thought. You're going to go into stat plot, second y equals. Hit enter on plot 1. Turn it on, utilizing the enter key again. Then you want the one that looks like a histogram. So I'm going to hit enter on the one that looks like a histogram. It asks you for an X list and a frequency list. All right? If you didn't put in a frequency table, then frequency stays at 1. The X list, generally should just be L1 unless you chose to put the data in a different list. No reason why you should, because this is the first problem. So this is the settings that we want, or the set of settings. I'll just chuck that up there somewhere. I guess I gotta have it a little visible. Undo. Fat finger strike again. All right, so then zoom 9, that's zoom stat. Just, again, be careful of the alpha lock. That's what the graph would look like if you let the calculator decide on scaling. I don't know that this is necessarily the scale that I want. Although it's appropriate, it's just I don't know if it's what I want. So I'm going to hit trace, and I'm going to have a look at it. Yeah, I'm not going from 12. I'm not creating an interval from 12 to less than 14.583 repeated. So I'm going to make a quick change here. So we go into Window, and change your scale, your X min, X max, and X scale to more convenient values. All right, your X min should be a value that you know is lower than the lowest value in your data set. So you could look back to the raw data, which is in decreasing order. You see the lowest value is 12 and the highest value is 27.5. You want your lowest value to be smaller than the smallest value in a data set. So you can go 0 on that if you want. You can go 10 also. Doesn't matter. I'm going to go 0. And you want the largest value, your X max, to be larger than the largest value in the data set. All right, so they have it at 30.808. How about just 30? Let's not make this any more complicated than it needs to be. And then when you're looking at your X scale, you want to have even increments going from 0 to 30. So definitely not 2.583 repeated. You can go but 2.5 if you want, but how about like 3 or 2? Go by 5s if you want. It doesn't matter. Just pick something that's not that. You know, something a little bit more round. All right. So I'll go by 5s. You can't go wrong. Honestly, you really can't go wrong because I look at your data and your parameters, and if they're reasonable, then you're fine. So yours does not have to match my answer key. So I'm going by 5s here. If you went by 2s, I just evaluate your work and make sure that it's all correct based on your decisions. That was your question. All right. So then now I'm going to hit graph. So you don't want to hit the zoom business again because that's just going to bring you right back to square one. So just hit graph, and now you should have a histogram. I mean, I'm not going to guarantee that it's going to look great, but it should have the parameters that you stated. I also have that stray red line there. That's from the previous example. If you come up with a stray line, you could leave it or you could take it out. It doesn't matter. I'm just going to clear it out because it's distracting. So I just need to get this on paper. So what I do is I hit trace, and you see that we have the nice even intervals of 0 to less than 5. Which contains 0 values. Hit the right arrow, 5 to less than 10. Also 0 values, which means that we don't even have to create these intervals on our graph if we don't want to, because they're just going to have intervals with no height. All right, 10 to less than 15 has 10 values. Right arrow, 15 to less than 20. $11 values. 20 to less than 25. And then 25 to less than 30. So 4 and 3 respectively. 4 and less than 3. Right? So I just got to get that on paper. All right? So going up to 11 is not a big deal. We can go by 1s. If you don't label any tick marks, it's assumed to go by one. So that's fine. You could just leave them unlabeled because we're only going by ones. So when you're going by something other than one, that you want to make sure that they're labeled. Then I have a total of 7 intervals, it looks like. 6 intervals. So space it out properly. And now I got to write this stuff in here, so we'll see you in like 20 minutes, I guess. I'm going to lose my mind here. Try to remember how I did it last time.
I can learn to understand you much better if I can get familiar with the way you talk. I need your
Shut up. Let me do Bluetooth. Well, I don't know which one it is. Well, I apologize if I'm about to add one of your devices to the computer. Nope. Nope. Wait, it says it's paired. Wait, that's me. This should be working a lot better then. Alright, well, it's not, so here we are. Garbage. Alright, anyway, I just gotta keep on plugging, I guess. $25. That's what I wanted to write. Well, that sucked. Alright, so height of 10. $11. 4, 3. Throw a couple of zeros here for good measure. They don't need to be there, but just you feel like we've accounted for everything. So that's good enough for full credit. So you can see just how awful your graph can be and still get full credit. I recommend you put the numbers in just because, especially if the sides aren't labeled, if it looks like it's at a certain height, and I can't tell, I'll always default to what you write in the bars. All right, so that's just a better way to do it. Boxplot, very straightforward. Stat calc 1. Our data is just an L1, so we go right to calculate. We need a 5-number summary. The calculator will create the graph also, but we need the numbers one way or the other, and since it's going to display it right here, why not just grab it from here? You know, so you could go either way with it. but we'll look at the picture also in a minute. But I have 5 blanks here for the 5-number summary. That would be these values. All right, so those values would go in there.
Frequency list would just be 1, right?
Frequency list would be 1, yep, unless you put it in a frequency table, which on this test you won't. All right, so I want to create a scale that's just like the previous graph. I'm going to be lower than the lowest and higher than the highest. So I'll go from 10 to 30. I'm sorry, I'll do 0 to 30. 10 to 30 would have been fine, but just for a little extra wiggle room, 0 is the nicest number. Why not get it in this set? 15 is right smack in the middle. Break that up into thirds. It's kind of a natural break there. So you do need to have an incremental scale. So I went by 5s here, but you could have gone by 1s if you wanted, but I think that's just making things unnecessarily complicated. So plot a point for 12. 13.75, I guess would be about right. Yeah. 17.45 right about meh. 19.9 right about meh. And 27.5 would be right about meh. Alright, so just get a nice little box going around the second value and the fourth value, and a vertical line through the third one, and just extreme it out. So line segments going out to the most extreme values in the data set. And that would be your box plot. If you want the visual, second y equals, you just go to the one that looks like a box plot. We'll talk about the modified one in a minute. All right, so go to that one and just hit zoom 9. It should look pretty much the same. If you want the values off of this, you just hit trace and scroll left and right. So the benefit of doing it this way is you get the visual and the numerical, but the other way is, I think, is just quicker. And besides, with the other way, you get all the other stuff too. So I'll pretend I just went through the process. I got all these values, right? I'm scrolling up and down. Well, the next question is asking me for the mean, median, mode, all that good stuff. So I have that in this display anyway. So this one really is one-stop shopping. So you can kind of take care of 2 questions for the price of 1. All right, so the mean would be 17.4. The median is the double dip because we needed it for the last question, but it's asking for it again, so 17.45. All right. The mode, you're not going to get that off of a display or through, the calculation. So we'll just have to eyeball that in a minute. The range is the difference between the max and the min. So we're looking at 15.5. All right, because that's max minus min. The mid-range, I mentioned this when we first talked about this concept. This is the trickier one because people tend to think, well, just take the range and chop it in half. This is the average of the max and min. So this is max plus min over 2. All right, so we want to crunch those numbers. I'm taking my 12 and my 27.5, adding them together and dividing by 2. So 19.75. Sample variance, sample standard deviation. It's easier to indicate the sample standard deviation first because that's given in the display. it's approximately, we're going to round to 3 significant digits here, so 4.351, but we don't want to use the rounded value in order to get the sample variance. What we want to do is compute what Sx squared would be. All right, and so to get that, we hit vars. And you're going to select statistics, so option 5. I'll write statistics. So vars, option 5, and then you just grab the Sx, that's option 3. All right. Now I want to square that. So use the power of 2 key. Or you can use the caret key and type in a 2, it doesn't matter. But square it. All right, so not square root, but square. Power of 2. Hit enter, and it'll square the unrounded form for you. Which, you know, ultimately I'm going to round anyway, but it might have introduced enough variation to give a different answer, so I don't want to take the chance, and neither do you. So this is the way you do it. And in the past, you know, like I'll answer the question that you may have never had any intention of asking. How am I supposed to remember that? You're not supposed to. You have the index card, 3 inches by 5 inches. All right, so you write that down. All right, so that's the idea. All right, anything that you think is not intuitive on the calculator, double-sided, yeah. Yes, double-sided, but handwritten only. As for the mode, let's just go back and take a look at the data and see if there's anything that repeats more than the 21, because it looks like the 21 appears twice. Anything that would repeat more than that would be the mode, otherwise the 21 is the winner. And it looks like that's our winner, because everything else seems to only appear once. All right, so it's just eyeballing it. Now, there are ways to let the calculator do this, but it falls into the category of making things way more complicated than they need to be. You got a 20? And you got the same sample standard deviation? And you did the Sx squared? Oh. Yeah, so vars, statistics, option 3, and then just squared. That's weird. Everything else is the same except for that one? I'll have to take a look later, because I honestly don't know how that could have happened. Sometimes people would just go with the rounded form and square that, and that screws things up, but even that wouldn't do it. Yeah, I don't know. Just curious. Nah, even if you selected the wrong one, it would still come in the same neighborhood. Yeah, that's weird. What are they going to say? Something. Normal distribution. Determine if the data are normally distributed. Show all work or included a detailed explanation. The detailed explanation doesn't actually have to be overly detailed, just somewhat detailed. Just explain. All right. The recommendation here is that you would use the normal probability plot. The other option would be to use the empirical rule. My sense is that that's not what you want to do, right? Because if you were to do that, you would probably run out of room here. So why not just do it this way? So normal probability plot, stat plot. It's the very last one. This is the technique where I showed you how to do it by hand. We created that big table just to get across the underlying concept, but with the idea that you would never actually have to do it by hand, right? So all we're looking for is a linear looking graph, right? So we have this display. That doesn't look good. It doesn't look good at all. How about that? A little bit better. So you're going to do that, and then zoom 9. And this is what we end up with as a graph. All right. A rough sketch, if you're doing it this way, just give me the roughest sketch of this graph. Like no scale or anything like that. Just start dotting it up, and then make an indication that since this does not form a linear pattern, your original data set would not be normally distributed. All right. So I somehow have to write this. Since plot is not close to linear, original data set not close to normal. Because we say things like close to or approximately or kind of, sort of, I wouldn't. I mean, you can. It's not out of bounds. You're allowed to use it. It's just we answered this question in like 30 seconds, whereas that would take more than that. So outliers and unusual values. So where in the last problem, in number 4, you didn't have to use the empirical rule. Here, you're going to have to use at least one aspect of it. So you're still on the hook for the concept a little bit. It's just you don't have to do the full-blown empirical rule. So outliers and unusual values. This is a 2-pronged question. For outliers, very easy. What we do is we create a modified box plot looking for any stray points. So create modified box plot. For unusual, we're going to compute x bar plus or minus 2s. So that's x bar minus 2s. X bar plus 2s. All right. All of the stuff is still in there. We've been working off the same data all this time, so everything we need is ready to rock. So second y equals, we go to the modified box plot. That's the one that looks like a box plot with a couple of stray points. It's kind of the idea. It's giving you an indicator that, oh, this is the kind of box plot that would identify if there were any stray points. So those are the settings that you're looking for there. You gotta make it like super tiny now, I guess. So mode. Zoom 9. This looks like the same box plot that we created on the previous page. There are no stray points. All right, it would be a truncated version of the previous box plot with a couple of loose points, maybe only one loose point because there could maybe only be one outlier. But here we're looking at a case where there are no stray points, so no outliers. No stray points. In the modified box plot. All right, no stray points in the modified box plot. So you don't need to redraw the box plot. We already have that. The only time you would need to include a new sketch is if the modified box plot was different than the original box plot. So if there was an outlier, basically. All right, so we got that. If there's an outlier, it'll isolate that outlier from the point. And so I can plot I'll show you real quick. I just got to remember to change the data back. Let's make this, that's going to be too big. I was thinking about that. It's going to be too big. It's going to make everything like super tiny. Let's make it like 127.5. All right. So here's your outlier. Here's everything else without the outlier being connected to it. All right, so this is a clear example that whatever this number is would be an outlier. All right, so now we need the unusual values, if they exist. So vars, statistics. So it's the same menu that you would go into to find the SX. We're just doing it for X bar and SX. So option 5. I need X bar minus 2 times SX, so vars option 5, and then option 3. So that calculation. Go to, or they screw up. Let me do the stack calc 1 again. Alright, so that's in vars. I might have hit something. Option 5, option 2, minus 2 times vars 5, 3. There it is. And then just a quick second enter, changing your minus into a plus. And so this would be our usual interval. I'll just jot this down here. So we're talking the usual suspects. That's going to be the interval of 8.698. Oh, Lord have mercy. 26.102. All right, those are the usual values. So anything that falls outside of that interval would be considered unusual. I know I don't have any value that's less than 12, so the low bound I'm not concerned with, but I know I do have a value that's more than 26. So I would be looking at my data. So 27.5, 26.9, 26.4, those are all bigger than this 26.1. All right, so these values would all be considered unusual. All right, so let me just snip it. Oh, wonderful. Control Z. Try to paste. I accidentally hit delete. Alright, so these are my unusual values. This is the top 3. So there's nothing that's so extreme that it would be considered an outlier, but there are enough that I just call them eyebrow raisers. Like the raising kind, not the cutting kind. So these are unusual values. So the snow accumulation on these particular days were high enough to be considered unusual, but not high enough to be considered outliers, right? An outlier, we look at that as kind of the sort of number that you would see, you'd look at it and say, oh, that shouldn't be there. Was this data from Minnesota? Like, where do these numbers come from, you know? Like, they really pop off the page at you. This is more like, whoa, those are pretty big, you know, but not exceptionally large to the point where it would be a problem. All right. Number 6 is the first instance where we move away from the given data set. Aiden is currently enrolled in 2 different math courses this semester with the same teacher. Recently, he took a test in both classes, and his results are as follows. In Calc 1, he earned a 99 with a class average of 85.76 and standard deviation of 9.59. In statistics, he earned a 73 with a class average of 75.64 and a standard deviation of 11.84. In which course did he perform better relative to the rest of the class? Justified by showing all computations. Now, relative to the rest of the class, we know that he performed better in Calc 1, just by looking at the problem. He got a 99, the class average was an 85-ish, whereas in statistics, he got a 73 and the class average was a 75-ish. So he's above average in one class, below average in the other class. So it's clear that, I mean, and besides, I mean, look at the numbers. I mean, they're huge. He got a 99 with a class average of 85.76. That's just a deviation. Forget about standard deviation. I'm sorry, relative standing value, z-score, just a deviation of about 14 points above average, right, as opposed to 2 points below average. So it's pretty clear which class is performing better in, but what the computations are calling for are z-scores. We have z-scores for calculus, and we have z-scores for statistics. All right, he got a 99. His score is a 99. Class average is 85.76. This is real data, by the way. This actually happened last semester. Student was taking my 2 classes, or 2 of my classes. Yeah. I don't protect the innocent. Yep, 6-4. I gave him his test paper back and I said, by the way, you just became a word problem. It's like, I don't know how to take that. I didn't know how I meant it, so it's all good. Nice guy though, so I meant it in the nicest possible way. Just making sure I typed in everything correctly. So we're looking at about 1.381. So he's 1.381 standard deviations above the mean for Calc 1. So his score is high, but it's not unusually high. He'd have to have a z-score higher than 2. That didn't happen, but still, not 99. That's nothing to sneeze at, you know. Sign up for that right now. And here we get a z-score of negative 0.223 approximately. All right, so then just a final statement, just kind of tying these numbers together and saying this is what they mean. So Aiden performed better relative to his calc class than his stat class because, very simplistically, 1.381 is a larger z-score than negative 0.223. All right, not looking for a literary masterpiece, just something that gets those numbers involved and also addresses the concept of, I'll call it relativity, but it's not, that's not really what it is. That's a different thing, but yeah, you got to have that term in there because we already know. I mean, it's not really a statistics problem if I say, in what class did he perform better? You know, like, I mean, that's not even grammar. But, you know, like a 99 is larger than a 73. We know what class he's doing better in. It's a question of relative to the remainder of the class, like where is he at? Right? So he's above average in the calc class and below average in the stat class. All right. Last question. Get you all out of here. Scuba divers have a maximum dive time, or have maximum dive times that cannot exceed when going to different depths. The data in the table below showed different depths with the maximum dive times in minutes. All right, so context is wonderful, but we still have to type the data in. So this is one of the, like, when you're taking the test, take one last look at your data set. Make sure that you absolutely don't need it for anything else, not even to check your work, because once you hit clear, there's no undo, and there's nothing more frustrating during a test, so I've been told, than a person prematurely deleting the data and saying, dang it, I needed that, so make sure that you're done with it before you delete it, or clear it, I mean to say. I never root for a meltdown during the test, but somebody's going to have one. The class size is large enough that it's almost guaranteed. So it's almost always because of something like that. It's never because of the math. Now this concept should be pretty fresh. So, but one thing you'll notice is that this question did not ask for you to create a scatter plot. That's the trade-off. Some questions will ask you to create the graph sometimes, and then some will ask you to find x given a particular y value. So you got to be prepared for both types of questions. That's why I took so much time to go over that homework problem book in the beginning of class, because that could end up on there. All right. Determine the line of best fit. Easy enough. Stat, calc, 4. Just make sure you store the regression equation in for y1. Alpha trace y1. It's just one of those things like if you take the time to familiarize yourself with the process on the calculator, this is not going to be a challenging question for you. All right? It's just the folks who come in with a blank slate. They're like, I meant to study all this calculator stuff, I just didn't. That they're staring at a test paper with really no hope. All right, so stating my equation in the proper notation, y hat is equal to negative 1.114 times x plus 127.238. All right. This one's asking for coefficient of determination. The previous problem we did was asking about correlation coefficient, so we're going both ways with this. All right. So coefficient of determination is your r squared, and we know that the closer that value is to 1, the better the fit. So r squared is equal approximately to 0.927. Alright, so I'll just type this. This indicates a very strong relationship between depth and dive time. Linear relationship. And again, throw an extra vary in there if you're not sure that you've kind of emphasized the strength properly. It could very, very strong. Alright? Very strong is good enough though. Alright. If it was like 0.99, I'd be in the very, very, right? Actually 0.95 or better is more like the very, very. 0.99 is your damn near. Like that's damn near perfect, you know? So a very strong linear relationship between depth and dive time. Estimate the maximum dive time for 110 feet. All right. So this is all calculator ready because we stored it in Y1. We need the dive time. So I'm just going to do a quick second. I like to look at the scatter plot also, although you don't really need it. I just don't want to be looking at a box plot while I'm also looking at a line. So I'll change my plot to a scatter plot. L1, L2 is the default. Zoom, stat, zoom 9. So that's my graph. It's pretty consistent with everything else that we did here. You know, 0.92. It seems like it's fitting the data. I just need to get the dive time, the y value for an x value of 110 feet. All right, so that's asking me to determine y hat of 110 feet. All right, so that's our alpha trace. Oh, sorry, I taught a different technique in here. Second trace value, type in your 110. Invalid. Okay, so this happens. Couple of things. One, just double check to make sure you typed it in correctly. But the other thing is, if your window is not large enough to accommodate that particular x value, then it'll return that error. So there's two ways to handle this. One, change your window so that it's a little bit larger. So make it like 120 for x max, and then hit graph. And then do the second trace value again. And it'll give you the answer. There's another way I'll show you now. I was debating whether or not to do it, but I'll do it. So we're looking at 4.667, I believe, minutes. Huh. Oh, there it is there. I was going to say, I didn't see it. So I usually, I'm a stickler about units.
How do you get 110?
Given.
Hmm?
Given?
Oh.
No problem, yeah. So another way to handle this would be, so if you get that error message, yeah. That's what I'm getting to, yeah. So the other way to handle it would be to do alpha trace in the home screen, alpha trace y1, and then type in the number. The benefit of doing it this way is that you don't have to worry about the domain or the window. This will work regardless. Actually, let me just get rid of this. This will work regardless of the window. All right, so you could do it this way. It's just calling up alpha trace, or calling up y1 using the alpha trace function in your home screen. All right. Either way is fine. The issue is if you have the domain issue on your graph, you know, like we did the Zoom 9, you do this technique, you type in the 110, and you're like, dang it, I don't know what to do. You forget about the window. You always have this option to fall back on. You do it this way if you have X and you need to figure out Y. Mm-hmm. If you have X and you need to figure out Y, this is the technique that you use. All right, so let me save this.